We will discuss some more questions of system of linear equations, and after that we will discuss vector spaces. This question was from GATE 2007 exam. Consider the system of linear equations x plus y plus z equal to 3, x minus y minus z equal to 4, x minus 5y plus kz equal to 6. Then the value of k for which the system has an infinite number of solutions is a part k equal to minus 5, b part k equal to 0, c part k equal to 1, d part k equal to 3. Try this.
k equal to minus 5, option A.
Yes, correct. So we know that this system has infinite number of solutions if rank of A is equals to rank of augmented matrix, and it should be less than number of variables. There are three variables. So augmented matrix is 1 1 1 1 minus 1 minus 5 1 minus 1 k 3 4 6. Now apply the row operations. R2 tends to R2 minus R1, R3 tends to R3 minus R1, 1 0 0 1 minus 2 minus 6 1 minus 2 k minus 1. R3 tends to R3 minus 3 times of R2. So this will become 1 0 0 1 minus 2 0 1 minus 2 and k plus 5 3 1 0. Now if k is equals to minus 5, then rank of A is 2, rank of augmented matrix is also 2. This implies rank of A is equals to rank of A augmented B, which is less than number of variables. So there are infinite number of solutions. So answer is option A. Now this question is from June 2015 exam, part B question. Let A be an M cross N matrix of rank N with real entries, then choose the correct statement. A part, Ax equal to B has a solution for any B. B part, Ax equal to 0 does not have a solution. C part, if Ax equal to B has a solution, then it is unique. D part, y dash A is equals to 0 for some non-zero y, where y dash denotes the transpose of the vector y.
For A और B तो नहीं हो पॉसिबल, तो डिस्कार्ड हो जाएगा. करेक्ट स्टेटमेंट चाहिए ना, तो सी और सी ऑप्शन.
Yes, C is correct. Solution. Firstly, see B part. Ax equal 0 does not have a solution. But I know that it has trivial solution, zero solution. Homogeneous system of equations always have a solution. So B part is wrong. And for A part, I can take a counter example. So if I take matrix A as 1 1 2 2 and matrix B as 2 3, then rank then augmented matrix will be 1 1 2 2 2 3. So R2 tends to R2 minus 2 R1, 1 0 1 0 2 3 minus 4 minus 1. So here rank of A is 1 and rank of A augmented B is 2. This implies rank of A is not equal to rank of A augmented B. So here I have taken m rows and n columns. This implies no solution. And it was saying that Ax equal to B has a solution for any B. So option A is also discarded. 1 second. This example can't be taken now because there are number of variables are 2 and it means rank of A should be 2 because it was given that rank of A is n. So instead of this example I should take the correct one. This will not be correct na because rank of A is coming to be 1. It should be 2 because it is given in the question. So I can take the matrix A as 1 0 0 1 0 0. Now here 3 cross 2 and rank of A is 2. So now it is fine. So I can take V as 0 0 1. Augmented matrix 1 0 0 1 0 0. Rank of A is 2. Rank of A augmented B. It is 3. This implies rank of A is not equal to rank of A augmented B. This implies no solution. Is it clear?
Yes, ma'am.
Now D part. Y transpose A is 0 for some non-zero Y where Y transpose denotes the transpose of the vector Y. If I take matrix A as 1 1 0 0 and Y as 1 0, then Y transpose A 1 0 into 1 1 0 0. So this will be 1 1. It is non-zero, but it was saying in the option that Y transpose A is 0. So option D is also discarded. So correct answer is option C. Ax equal to B has a solution, then it is unique. Do you know the reason why? I know 3 options are discarded,
Yes.
but what is the exact reason for this? That why Ax equal to B has a solution, then it is unique because rank is given as n. Rank is full, na? Rank of A is n and
Yes,
n
ma'am.
is number of variables. Whenever rank is full, then it will have unique solution. Now this question was from December 2017 exam. Again part B problem. Let A equal to 1 1 2 minus 1 1 3 1 1 alpha and B equal to 1 3 beta, then the system Ax equal to B over the real number has A part no solution whenever beta is not equal to 7, B part an infinite number of solutions whenever alpha is not equal to 2, C part an infinite number of solutions if alpha is equals to 2, D part a unique solution if alpha is not equal to 2.
D option.
Yes.
Unique solution if alpha is not equal to 2.
So A augmented B is 1 1 2 minus 1 1 3 1 1 alpha 1 3 beta. So R2 tends to R2 minus R1, R3 tends to R3 minus 2 times of R1, 1 0 0 minus 1 2 5 1 0 alpha minus 2 1 2 beta minus 2, R3 tends to 2 times of R3 minus 5 times of R2. So after this, how you have done?
For unique solution, rank of A and augmented matrix B should be same. So alpha is not equal to 2. So first column and third column, if they would be same, no, then it will be. See, I first and third first and third column. They are coming out to be same 1 0 0. So if alpha minus 2 is also 0, then they would become same. So rank will reduce to 2.
Yes.
Rank of A will reduce to 2, no?
Yes.
So alpha is not equal to 2 for unique solution.
Or you can use one more thing, that whenever I need to check for unique solution, then determinant is non-zero for both homogeneous also and non-homogeneous also. Here system was non-homogeneous, so determinant should be non-zero. Means determinant will be A was 1 1 2 minus 1 1 3 1 1 alpha. Now for unique solution, determinant should be non-zero. This implies 1 into alpha minus 3 plus 1 alpha minus 2 plus 1 3 minus 2 1. This should be non-zero. Alpha minus 3 plus alpha minus 2 plus 1 should be non-zero. So 2 alpha minus 5 plus 1 minus 4 should be non-zero. This implies alpha is not equal to 2. So this is method 2 to solve this. Because it is a part B question. But if it is part C, then I need to check remaining options also now. So A part, it is saying beta not equal to 7, then it will have no solution. So if beta is not equal to 7, are you getting same thing now? Calculation is correct now?
No, I am actually I have not replaced 5. I'm getting 100 minus 125 10 alpha minus 2 12 beta minus 2.
Okay.
I have not replaced 5.
Okay. So if beta is not equal to 7, then there are two cases. Either alpha can be 2 or alpha cannot be 2. So if alpha is equals to 2, then rank of A will be 2 and rank of augmented matrix will be 3, because beta not equal to 7. Yes, correct. So this implies no solution. But if alpha is not equal to 2, then rank of A will be 3 na? We have seen that if alpha is not equal to, then unique solution. So
Yes, ma'am.
rank of A will be 3 and augmented matrix rank will also be 3. This implies unique solution. And in the option it was saying no solution whenever beta is not equal to 7. But we are getting a case when unique solution is exist. So option A is discarded. Option B, an infinite number of solutions whenever alpha is not equal to 2. B part, if alpha is not equal to 2, then we have already seen that rank will be 3. Whenever rank is full, then unique solution exists. And option was saying that infinite number of solutions are there. So option B is also discarded. Option C, an infinite number of solutions if alpha is equals to 2. And we have seen that if alpha is equals to 2 and there is no restriction on beta na. So if beta is not equal to 7, if I consider this only, then I was getting no solution. So option D is also wrong na. Option D, sorry. Option C is also wrong because it was saying infinite number of solutions. So answer is option D only. This was question number 7. JAM 2011 question. Find a value of C such that the following system of linear equations has no solution. X plus 2y plus 3z equal to 1, 3x plus 7y plus cz equal to 2, 2x plus cy plus 12z equal to 3.
There are two answers.
No, only one answer is there. There will be two values of C.
Yes, 10 and 3.
So augmented matrix is 1, 3, 2, 2, 7, C, 3, C, 12, 1, 2, 3. So R2 tends to R2 minus 3 times of R1. R3 tends to R3 minus 2 times of R1. So it will be 1 0 0 2 1 c minus 4 3 c minus 9 6 1 minus 1 1. Now R3 tends to R3 minus c minus 4 times of R2 1 0 0 2 1 0 3 c minus 9 and minus c square plus 13c minus 30 1 minus 1 c minus 3. So firstly I will solve this. Minus c square plus 13c minus 30 equal to 0. So from here c square minus 10c minus 3c plus 30 equal to 0. So c is 3 and c is 10. So this will be 1 0 0 2 1 0 3 c minus 9 c minus 3 c minus 10 1 minus 1 c minus 3. And I was asked in the question that for which values of c the system has no solution. So if c is equals to 3, then rank of A is also 2, rank of augmented matrix is also 2. This implies rank of A is equals to rank of augmented matrix, which is less than 3 number of variables. Means there will be infinitely many solutions. Means C cannot be 3. So C will be 10. We can cross check also. If C is 10, then rank of A is 2, rank of augmented matrix is 3. So rank of A is not equal to rank of augmented matrix, means no solution. Now is it clear?
Yes, ma'am.
Okay. The system of linear equations x minus 5 plus 2z equal to b1, x plus 2y minus z equal to b2, 2y minus 2z equal to b3 is inconsistent when b1, b2, b3 equals a part 2 2 0, b part 0 3 2, c part 2 2 1 and d part 2 minus 1 minus 2.
It's C.
Yes, correct. So augmented matrix is 1 1 2 minus 1, sorry, 1 1 0 minus 1 2 2 2 minus 1 minus 2 b1 b2 b3. So r2 tends to r2 minus r1, then we will get 1 0 0 minus 1 3 2 2 minus 3 minus 2 b1 b2 minus b1 and b3. Now r3 tends to 3 times of r3 minus 2 times of r2, 1 0 0 minus 1 3 0 2 minus 3 3 into minus 2 minus 6 and plus 6 0 b1 b2 minus b1. So this will be 3 b3 minus 2 b2 plus 2 b1. So I can write it as 2 b1 minus 2 b2 plus 3 b3. Now I want to find inconsistent. Solution is inconsistent if rank of A is not equal to rank of A augmented B, augmented matrix. No solution, na? So I need to check that 2b1 minus 2b2 plus 3b3, this should be non-zero, na? Then only system will be inconsistent. So A part 2 2 0. So 2 into 2 4 minus 6 plus 3 into 0. So 1 second, this was 4 0. Option A is discarded. Option B 0 3 2. So minus 6 plus 6 again 0. C part 2 2 1 4 minus 4 plus 3. This is non-zero. So option C is correct. And in option D also 2 minus 1 minus 2. 4 plus 2 minus 6. This is 0. So answer is option C. And practice more questions from Dr. A.P. Singh Sir book. Now next we are starting with other topic.
Ma'am, you will send the PDF for that book also?
Linear algebra. Okay, I will share.
Yes.
Vector space. So do you remember the definition of vector space?
Vector space, it has scalar and vectors, and there is group properties, field properties, addition, commutative, associative.
Yes, with the
But
addition it forms a abelian group.
yes, ma'am.
With addition it forms a abelian group, na?
Yes.
So let f with respect to two operations plus and dot, addition and multiplication, this be a field. The elements of f are called scalars. Let V be a non-empty set whose elements are called vectors. Then V is a vector space over a field F denoted by VF, means vector space V over field F. If A part, there is internal composition in V called addition of vectors, which is denoted by plus, such that for this composition V, is an abelian group. So it will satisfy the 5 properties for an abelian group. First one, closure property. If I take two vectors v1 plus v2 belongs to vector space V, for all v1 v2 belongs to V. Second property, associative property. If I add v1 and v2, then I add v3, it is same as v1 plus v2 plus v3. Third property, existence of additive element. There exists an element 0 belongs to V such that V plus 0 is equals to V equal to 0 plus V for all V belongs to capital V. This element 0 belongs to V is called the zero vector. And I can also say that with respect to addition, 0 is our identity. Fourth property, existence of inverse element. Or with respect to addition, additive inverse. To every vector, V belongs to V, there exists a vector minus V belongs to V such that V plus minus V is 0 is equals to minus V plus V. Now after these fifth property is left, na, commutativity. Commutative property. Then only this will be an abelian group with respect to addition. V1 plus V2 is equals to V2 plus V1 for all V1 V2 belongs to capital V. Now after these 5 properties, it need to satisfy one more property, which is scalar multiplication property. there is an external composition in V over F called scalar multiplication and is denoted multiplicatively. That is, alpha V belongs to capital V, means we will take a scalar and a vector. Their multiplication is known as scalar multiplication. For all alpha belongs to field, scalar comes from field, and vector belongs to this capital V set. In other words, we can say that V is closed with respect to scalar multiplication. Now, it need to satisfy four more properties. The two compositions, that is scalar multiplication and addition of vectors, satisfy the following conditions. First property, alpha into v1 plus v2 is equals to alpha into v1 plus alpha into v2 for all alpha belongs to the field and v1 comma v2 belongs to v. Second property, alpha 1 plus alpha 2 into v is equals to alpha 1 into v plus alpha 2 into v for all alpha 1 alpha 2 belongs to field and v belongs to capital V. Third property, alpha 1 into alpha 2 into v is equals to alpha 1 into alpha 2 into v for all alpha 1 alpha 2. These belongs to scalars. These are scalars, so it belongs to field and v belongs to v. Fourth property, 1 into v is equals to v for all v belongs to capital V. 1 belongs to field and 1 is the unity of field F, or I can say that 1 is the multiplicative identity. So by these four properties and fifth one and these five, by these 10 properties I will say that V is a vector space over F. But in the exam you don't need to check these 10 properties. I am telling a short trick for this, because to check these properties it will be very lengthy na. So how to test a vector space? Firstly, it should be a abelian group with addition operation. Second property, F with respect to plus and dot should be a field. Third property, V cross F is mapped to V again. Fourth property, those last four properties For example, these are type 1 examples. If V is real with plus and field is defined as real with plus and dot. So first property, real with respect to plus is abelian group. Real with respect to plus and dot is field. Third property, real into real. We'll go to real again. Fourth property, all four properties will also be satisfied. Therefore, V over F, which is written by R over R, is a vector space. Second example, if I take V as real with respect to addition over field rational with respect to plus and dot, tell me whether it is a vector space or not.
Ma'am, how to proceed it?
You simply need to see like this, na, that V with respect to addition is abelian, then field,
Yes.
then you can see na that
Q is a field.
yes, R with respect to plus is abelian.
Yes.
Second, rational with respect to plus and dot forms a field. Thirdly, real into rational. So if I multiply some real number with a rational number, then it will be again a real number only, na?
Mhm.
And lastly, all those four properties will be satisfied. These four properties. There will be no issue in this, na? Multiplicative identity of
Mhm.
real will also be 1.
Yes, ma'am.
Third example. Now my vector space, sorry, now my this set of vectors V is rational with respect to plus and field is real. So firstly, rational with respect to plus will form my abelian group. Real is a field. Now third property, rational into real should go into rational. Is it possible? If I take any rational number, say 1 by 2, any real number, root 2 is also a real number. So their product will be root 2 by 2. This is not a rational number, na? So third property is not satisfied. Therefore, Q over R is not a vector space. Is it clear?
Yes, ma'am.
So are you able to see what is this property? This is like scalar multiplication only, na? Alpha into V should again belong to V. Alpha is from field and this vector is from capital VZ. So by this only I have written this map, na? So next example, V is equals to singleton 0 with respect to plus and field is real with respect to plus and dot. Now check this example also.
Here multiplicate with respect to addition. Okay.
Hmm.
So it is a vector space.
Yes.
Because 0 cross R is 0 again.
0 with respect to plus is an abelian group. Secondly, real with respect to plus and dot is a field. Thirdly, singleton 0 cross R. It will again be singleton 0 because if I multiply any number, any real number with 0, then it will be 0 only. Lastly, all four properties are satisfied. Therefore, V over F is a vector space. Now I am going to tell you another trick. So in the first example, you can clearly see that field was contained in vector space. Here also field was contained in vector space. In both the cases it was vector space, but here the problem was vector space, set of vectors was contained in field. So this was a problem. So trick is for this only, that V star F is a vector space if field is contained in V star. V star is non-zero abelian group and F is a field. And this trick is valid only for usual operations. Now I am writing some more questions. Try this and tell me. Check whether the following are vector spaces under usual operation. R over complex, R over Z, R over R plus, rational over C, rational over Z, R plus over R, Z over Q, Z over R, complex over real, complex over rational. Try this, I will be back in a minute.
In this case, first option is wrong. Second is correct. Fifth is correct. And,
how
9, 10
one
is
second.
correct.
How come second is correct?
R cross Z. Then it will be a real number. Z is also real. And
But Z
R,
is not a field, na?
oh yes, Z is not a field.
Hmm.
So QZ is also not there.
So first one, is
It's wrong.
violated because of this trick only.
So only 9 and 10 is correct.
Yes, only 9th and 10th are correct. So in the first one, trick is not satisfied. Na?
Yes.
Real number is contained in complex.
Yes.
Second one, Z is not a field.
Mm.
And what about third?
Third is real into R plus. R into R plus cannot be always R plus. It can be R minus.
But first of all, R plus is not a field, na?
Yes, R plus is also not a field.
Because additive identity is missing.
Hmm.
Then fourth also trick is failing.
Yes.
Fifth,
That
again
is not a field.
not a field. Sixth,
In this case, R is a field, but R plus into R is not always R plus. But R plus is not a vector space.
R plus is not a abelian group, na?
Yes, not a abelian group. Sorry,
Hmm.
it's not a abelian group. Not a field. Not a field.
Seventh, again trick is failing.
Yes.
Eighth, again trick is failing. Ninth and 10th, all the properties are satisfied, or I can say trick is satisfied.
Yes.
So only 9th and 10th are vector spaces. Now type 2 for matrices. V is n cross n matrix like this, and field is real with respect to plus and dot. Now here also it can be easily checked. First property, m n cross n with respect to addition, this will form a abelian group, na? Because closure property will be satisfied, then associative property will also be satisfied. Matrix addition is associative, and identity element will be the zero matrix. Inverse will also exist. Commutative property is also satisfied, and R with respect to plus and dot is a field.
So we have to take M n cross n as non-similar matrices if inverse exists.
But here the operation is addition, na?
Yes. Okay. Right.
Then m n cross n R into R will again be a matrix only, na? If I multiply any scalar, any real number with this matrix, then it will be again a matrix. And also all the row properties are satisfied. And for the last property, multiplicative identity will be, if it is 2 cross 2 matrix, then it will be 1 1 multiplicative identity. What will be multiplicative identity? 1 into, it is like this, 1 into A should be A. A is an n cross n matrix.
Identity matrix.
Identity matrix. So like this, if second example is here, V is Mn cross N rational with respect to plus and field is rational with respect to plus and dot. First property, V with respect to plus is an abelian group. Second property, rational is a field na? This is field also. And third, Mn cross N R into rational number. If I multiply a matrix with a rational number, then it will be again a matrix also. And last four properties are also satisfied. So it is a vector space. Now check this. V equal to Mn cross N rational with respect to plus over field equal to real with respect to plus and dot. So tell me whether it is a vector space or not.
V is not a Bayesian group because यहाँ पे additive identity minus will not exist. नहीं, okay, sorry. Rational number with plus additional negative तो आएगी. Yes, it is a vector space.
Are you sure? The trick is valid for this, na?
Field is contained in vector space. The field is not contained in vector space. Yes.
So it is not a vector space. Or you can say like this, that Mn cross Q into R will not be mapped to Mn cross Q, because if I take any matrix, any rational matrix, say identity matrix only, and if I multiply it with root 3, then it will be root 3 0 0 root 3. Now this matrix does not belongs to Mn cross N rational, because entries are not rational, na? They are irrational. That's why it is not a vector space. Okay. Now type third in the form of tuple. First one, V is equals to Rn x1 x2 so on till xn, such that xi belongs to real numbers with respect to addition. Field is R with respect to plus and dot. Now first property, Rn with respect to plus will form a abelian group. Second property, R with respect to plus and dot forms an field. Third property, V cross F should go to V. So elements of V are of the type n tuple x1 x2 so on till xn, if I take scalar as alpha, this will be alpha x1, alpha x2, so on till alpha xn, and this belongs to the vector v Rn. Fourth property, all the four properties will be satisfied. Therefore, Rn over R forms a vector space. Second example, check and tell me Rn over Q. Here also you can apply the trick.
Yes, it is a vector space.
Yes. Third, Qn over R.
Not possible because R is not contained in Q.
Yes, R is not contained in Q, so not a vector space. Now next is one example. If V is R square with respect to addition over field R with respect to plus and dot x comma y plus x1 comma y1 is equals to x plus x1 comma y plus y1 and c x comma y is equals to cx comma 0. Now with these operations I need to check whether V over F is a vector space or not. Firstly check it yourself, after that I will discuss.
So this is a vector space over F.
No, it will not be a vector space.
P X Y. Is it
So firstly R square with respect to addition will be an abelian group. Firstly trick will fail here na, because operations are not usual. This is unusual operation. This is okay, but here if it is if scalar is multiplied by x comma y, then it should be cx comma cy, but second entry is 0 na, So that's why it is not a usual operation. So here I need to check every step. So R with respect to addition and multiplication will form a field. Thirdly, V cross F will also be in V. R cross R will belong to R square only. Now this, in those four properties, the last one, 1 into x comma y should be x comma y according to that property. But here 1 into x comma y will be x comma 0 by this, because it is defined like this only, na? Cx comma y is equals to cx comma 0. So this property is violated. That's why this is not satisfied. So it is not a vector space. Therefore, not a vector space. Now is it clear?
Yes, ma'am.
Okay. Now next is type 4. Let S be any non-empty set and let capital K be any field let V be the set of all functions from S to K, that is B is equals to function such that F is a mapping from S to K. Let the sum of two elements F and G in V be defined as follows. F plus G x is equals to Fx plus Gx for all x belongs to S. Also let the scalar multiplication of an element F in V by an element C in F. F is a field. This be defined as follows. Cfx is equals to Cfx for all x belongs to S. Then V forms a vector space over F where F is equals to K, or F is any subfield of K. For example, B equal to F such that F is a mapping from 0, 1 to complex numbers. So here S is this interval 0, 1, K is complex numbers. Now I need to check whether this B is a vector space over complex numbers, over real numbers, and over rational. Means field is complex numbers, field is real numbers, and field is complex numbers. So just a small thing, field should be contained in K, because it is mentioned that either field is K or F is any subfield of K. Now here F is equals to K, so it is a vector space. Now here field R is contained in K, again a vector space, because here also trick can be applied na? And here field rational is contained in K. K is complex number, so it is again a vector space. Is it clear?
Yes, ma'am.
Okay. Now some examples. If I take like this, V is equals to F such that F is a mapping from 0, 1 to real numbers, comma F is continuous over a field real number. Now tell me whether this is a vector space or not.
Well, F is R and the image of V is also R. So
Yes, it is a vector
contain.
space.
Yes, it's a vector space.
All the properties will be satisfied, and first property is also satisfied, that closure property with respect to addition, because sum of two continuous functions is again a continuous function. Now second, V is equals to F such that F is a mapping from 0, 1 to real such that F is discontinuous. Whether it is a vector space or not.
No, because sum of discontinuous function can be continuous. Was it that? May or may not be continuous.
Sum of two discontinuous functions need not be discontinuous. It may be continuous. Can you give me any example for this?
नहीं आ रहा तुम्हारे लिए कुछ डिसकंटिन्यूस में अगर हम वो भी ले ग्रेटेस्ट इंटीजर फंक्शन 1 एंड अदर मोड फंक्शन ले
या फिर ऐसे कर सकते हैं कि एफ एक्स को अगर मैं ग्रेटेस्ट इंटीजर फंक्शन ले लूँ और जी एक्स को I can take x minus greatest integer function, then
हाँ ये हो सकते हैं
f
then
x
sum will be
plus
x
g x will be x and it is clearly continuous. So
Yes.
closure property fails.
Mhm.
Therefore, it is not a vector space. Now some more examples. Now this is type 5. V is equals to sequence an such that an belongs to real numbers. So if it is a sequence, I can define it as function f only, and its domain is natural numbers to real numbers, and field is real numbers. So tell me whether this will be a vector space or not.
Um, yes, I think because
Hmm.
sum of two real is real.
Sum of
Natural numbers,
two
it will be.
I can say
Yes.
na sum of two sequences is again
It's
a
again
sequence.
sequence. Yes.
All the properties will be satisfied. So it is a vector space. And if I take an as a convergent sequence, so this is also a vector space because sum of two convergent sequences is again a convergent sequence, and scalar multiple will also be scalar multiple of a convergent sequence is again a convergent sequence. Identity will be a zero sequence. All the properties will be satisfied. Na? Field was real. Now third, and sequence an is a divergent sequence. What about this?
It is not a vector space.
Reason?
Again, sum of two divergent sequence can be convergent, may or may not be convergent. It is not always divergent.
Need not be divergent always.
It's,
Any example? It may be convergent.
like n and minus n.
Yes. Sequence an is n, sequence bn is minus n. Then they are divergent, but their sum,
Hmm.
it is zero sequence, which is convergent. Therefore, it is not a vector space. Fourth example, V is equals to sequence an such that an sequence an is convergent and it converges to 2. What about this?
It is not a vector space
Yes, it is not a vector space. Reason?
because sum of the two convergent sequence, then it will be 2 plus 2, 4. Limit will add. No?
Hmm. If sequence an converges to 2, sequence bn converges to 2, then sequence an plus sequence bn, this will converge to 4. I can write it as sequence an plus sequence bn. Then I can open it, and it was given that sequence an converges to 2. So closure property fails. Also, identity is not present. Absence of identity element, because here identity element will be 0 sequence, but it is mentioned in the in this vector set V that sequence an converges to 2. So this is not a vector space.